Okay, so for us to really see the evidence that this reaction is happening at the center of the sun, namely that the sun is shedding its mass and converting it to energy, we would like to verify that these neutrinos are indeed coming from the sun. But they don't interact very much with us. So as I said, there are 100 trillion neutrons going through your body every second. Do you feel the wind of neutrons coming from the sun? Nobody does. So it basically doesn't interact anything with anything. So that would be a challenge if you try to detect these neutrons coming from the sun. But there is a way. This is how to see these nearly invisible neutrinos. Basically, that neutrons have such a low probability to interact with anything, you need to build a big target. If the target is big enough, there may be some small chance that neutrinos might cause some reaction inside this big target. So you need something really big. And that's what people in Japan have done, namely to build a tank of 50,000 tons of water. And that's like 40 meters high. That's buried under the mountain. It's in a pitch dark underground mine. And with this tank, you hope to detect neutrinos coming from the sun. And what you see here in this picture are these little round things. And they may look very small, but it's actually a pretty big object called phototubes. It is this big. And just imagine that these big things are suspended on the wall all the way around, 11,000 of those. And you fill up this entire tank, that process by itself can take 4 months. It's a very big target to detect the neutrinos from the sun. So what I'd like to show you here is just to give you a sense of how big this object is. So if you look at the bottom of the tank, and that's how it looks like, and I'm just slowly moving the picture that you will sort of start to look up inside the tank, and eventually you get to the ceiling. And I hope you get an idea on how big this tank actually is by just moving this picture here. So that's how big it is. So using this very big tank of water, we'd like to detect the neutrinos coming from the sun. So as I said already, we believe the sun is burning atoms by fusing 4 hydrogen atoms into helium, and the neutrinos are the byproduct. And those neutrinos are going through our body every second, like trillions of them. They don't interact very much, so we don't feel them. But once you have a big tank like this one, there is some chance that neutrinos might cause some reaction. And even with this huge tank and so many neutrinos coming from the sun, it turns out that you may be able to see maybe 5 neutrinos a day. And so that's very hard to see. But if you just wait long enough, like 5 years, and keep recording these neutrinos coming from the sun time on time, eventually you can take a picture of the sun after long exposure. This is remarkable. This is the picture taken with neutrinos in the pitch darkness, 1 kilometer underground. But the neutrinos can penetrate the entire 1 kilometer rock very easily and can cause reactions, very small number of them. But by accumulating and wait for enough time, then you can take a picture of the sun underground. And it's even more remarkable is that this is a picture of the center of the sun where this nuclear reaction is happening. That releases neutrinos. This is not the picture of the surface of the sun, which we can see with our naked eyes. So this is the way we now have a firm evidence that inside the sun, indeed, you are forcing these elements to come together, fuse them together to build a bigger element, and that's what's happening inside the sun. And because it's such a remarkable experiment, the name of the experiment is called Super Kamiokande. We often call it short as Super K. And I was very shocked and surprised to actually find fortune cookies from Super K brand when I was just having a dinner at a Chinese restaurant in Colorado. So Super K, as you see, is very famous. Okay, so what that brings us to think about is the following question. Okay, Lord Kelvin was wrong. He was assuming that the sun burns based on chemical fuel, but that was not the case. The nuclear fusion is far more powerful than burning chemicals, so it's going to last a lot longer. So now we have a revised estimate how much the sun is going to last, and the answer turned out to be about 4.5 billion years. That's a big difference, right? So we don't have to worry about the sun sort of going out of steam in 1,000 years from now. It's going to happen only 4.5 billion years from now. But it will come to an end. And what would happen then is that there's no hydrogen fuel anymore the sun can use to power up. And once there's no power of the sun, then it can support its own weight. It would crush at the center of the sun. As a result, the outskirt of the sun would blow up. And it becomes much, much bigger to the extent that it might end up swallowing the Earth. That's how big the sun is going to become. It's called a red giant. So obviously, before this happens, we need to come up with an escape plan. We need to build a big spaceship or something. We go to some other planet in 4.5 billion years. That's certainly a subject of a research. So I hope you can get involved in that kind of research as well.